Very good afternoon. Come back to the afternoon session. I hope you have a good lunch. I'm already refreshed, so I'm not sleepy. But I don't mind if you sleep. Okay, so let's continue with basic topic number 3. So the next topic is congruence relations. So I hope you have, I hope you understand what we have been discussing this morning on the topic of divisibility and prime numbers. Okay, this is the. So if you go through any number theory books, elementary number theory books, so this should be the next topic, and elementary number theory, which is in congruences. And the definition is basically it's using the concept of divisibility that we have discussed this morning. So before I begin with that, before I go look at the definition, so let's just look through the history of this concept of congruences. So, theory of congruence was introduced by Carl Friedrich Gauss in 1777 until 1825. And his book, Disquisition Mathematica, so this is indicated from Stuart, 1987. But basically, the concept or the theory of this congruence is already known, or was known before that, which is the concept which is known by Al-Mizan, which has existed much earlier, and there is many errors. So if you can find some reference to that, so that would be good. So not basically the notation that Gauss used for the concept of congruence, but probably something similar to that. Okay, let's look at the definition. So that A and B be integers. So we say that A is congruent to B modulo a positive integer M. If M divides A minus B, and we write it as A with that notation, which we usually call it as congruence notation, A congruence to B on M. So this is the basic basic requirement for that definition, which is M must divide A minus B. So if A minus B is not divisible by M, so that we can say that it is not A is not congruent to B. So we have the notation similar to the first one here, but with the negation to the congruence symbol. Okay, so it is very simple to understand the concept of congruence. So it refers to the concept that we have discussed this morning, which is divisibility. Okay, let's look at some examples based on the definition that was given. So if you have two integers, 5 and 1, and M is equal to 4, so we can say that phi is congruent to 1 mod 4. Since 4 divides phi minus 1, so it is obvious based on the definition, so it is phi is congruent to 1. Then the second one, 2 is congruent to 7 mod 5, since 5 divides 2 minus 7, so obviously also from the definition. Then the third one, 14 congruent to 0 mod 7, since 7 divides 14 mod 0. And the last one, definitely 12 is not congruent to 1 mod 5, since 5 doesn't divide 12 minus 1. So okay, in terms of the definition, so we can actually, we've given any integers in some modulo of positive integer M, so definitely we can decide whether the two integers are congruent to each other. Okay, so based on the discussion this morning and some familiar notation, So if A is congruent to B1M, A is congruent to B1M if and only if there exists integer k such that A is equal to B plus Km. So you rearrange the equation. So bringing B to the right hand side, so we have A minus B equal to Km, definitely, which implies, according to the definition, M divides A minus B. So A definitely congruent to B1M. Okay? So the proof is very simple. So it is, we are using the definition. Okay. Now we go to some other concepts related to this congruence, which is these residues. So if you recall the division algorithm, so given an integer A and M, so there exists Q and R's, which is Q is the quotient, R the remainder, such that this equation is satisfied. Right? So this is how the division algorithm that we discussed is like. So A must be equal to Qm plus R. Okay. So the question is, what can you say about Q and R related to the division algorithm and the concept of congruence? So if it is related to the concept of congruence, so what does it say if you were to use it in the congruence form, right? So we have A congruent, so A equal to Qm plus R, right? So that is the normal, that is the division algorithm given any two integers A and M. So therefore we can rewrite the equation as A minus R equal to Qm, right? From this equation, right? So meaning that M divides A minus R, right? So based on the definition of the congruence, so we have A congruence to R modulo M. So if, let's say we are given a fixed M and any integer A, so if you were to divide A by M, so how many possibility of the remainder that we can get out of that division based on the division algorithm? So we have M integer, so M is picked, right? Then given an integer A, so we can pick any integer A. So if you were to divide A by M, so definitely by the division algorithm, we would be getting Q, which is the quotient, and the remainder, right? So how many possible remainders that we can get out of all the possible integers that we divide by M? There is only possibility. The only possibilities are this set of integers, right? Because according to the division algorithm, when we divide A by M, so the possible remainder is from 0 up until the integer that we divide, right, which is M. But it cannot be M, it must be at least one less than M, which is M minus 1. So these are the possible remainder, right, that we can get if we want to divide A by M. So meaning that given an integer A, so A will be congruent to exactly one of the integer in this list. Is that correct? So really not sure whether that's a correct statement. So given, let's say M is equal to 5, right? So given an integer A, so if you want to divide by 5, so we have 1, 2, 3. So what is the quotient of the division? So we have M, which is 5. So what is the quotient? So this is the divisor. 20, right? And the remainder is 3, right? So whereby according to the division algorithm, so this remainder must be between 0 and 5, right? 5. So the possible remainder, possible value of the remainder is 1, 0, 1, 2, we can perform it, right? Because it cannot go more than 5 because we are dividing by 5, right? So in modulo 5, so 1 would be the remainder when dividing by 5 is equal to 3. So based on the congruence form, so we can write this as 1 of these congruent to 3, 1, the modulus is 5. So this value cannot go more than m, which is 5 in this case. So it is the possible values of the remainder is the 5 values, which is 0, 1, 2, 3, and 4. So whatever integer you put here, so, no matter how big it is, so the remainder must be exactly one of those integers in this list, right? And we can also say that in the list of this integer, which is between 0 and 4, so none of them are congruent to each other modulo 5. So it is not possible for any of them to be congruent to each other. Because let's say we have 200 is 2 congruent to 3, 1, 5, so it is not possible, right? So 2 and 3 are exactly the list of remainders, so 2 cannot be congruent to 3, 1, congruent to 5. So if the integer is less than 5, so it is congruent to itself only. Right? Okay, so this integer, or this list of integers, which is between 0 and 4, when m is equal to 5 in our example, so we call it as the least residue of a modulo integer m. So if you take any integer a, so a must be congruent to this integer r, which is 0 and m minus 1, and it is the least residue. So there are some other integer which has the same residue, right? This residue, right? And there are some other integers which have different least residues. But definitely every integer must congruent to exactly one of these, right? Between 0 and m minus 1. So for example, so if you take m is equal to 5, so what is the least residue of 7? So if you are looking at the division algorithm, so we are doing the division, which is dividing 7 by 5. So we have the quotient as 1 and the remainder would be 2, right? So 2 is the least residue of the of 7, right? So we say that 7 is congruent to modulo 5. Okay, if we are taking m equal to 10, so what is the least residue? 271, so this is pretty obvious, right? Because modulo 10, so we are looking at the multiple of 10 that is divisible by 10, right? So the only multiple of 10 here which is possible is 270, meaning that 271 is congruent to 1 modulo 10, right? So the 1 is the least residue to 17 modulo 10. Okay. So question, how many integers have the same least residue of 1 modulo 5? So as I said previously, so there are many integers, right? But exactly how many? With least residue 1 modulo 5. So there are some integers which has the same residue as 6, right? 6 is congruent to 1, 1, 5. Because possible, yeah, we will take 1 as the least residue. So there would be some more integers which has the least residue of 1. So 6 is one of them. And then some other integers would be write it 6 equal to 1 plus 5k, some k. So we can actually generate all those integers by substituting k with the integer here, right? So let's say k is 0. So what do you get? So the residue is equal to 1. Sorry, other integers, integers which has this residue of 1 equal to 5, which is like 6 times 1. So k is equal to 2, let's say, so we have yeah. So it is, so the integers which have the least residue of 1 are 1 plus multiple of k, right? So 6, what else? So we just add 5, right? So 11 and some other. Yeah. So meaning that how many integers do we have which has this residue of 1? So it is infinitely many, right? So when we add 5 to the 6, so we'll be getting infinitely many integers which has the same residue as 6. Okay, so 6 and 5 are small numbers. So let's look at a big number. So what is the least residue of 230 to the power 61 modulo 11? So what is the possible values of least residue of mod 11? So we have 11 numbers which are 0, 1, 2, 1, 2, 10, right? So we know it is among those 11 numbers, which we start from 0. But which one is exactly the least residue based on the given number? 1. Okay. So why do you say that 1? Fermat-Little theorem. Okay. So does anybody else know what Fermat-Little theorem is? So if you don't know, probably we'll see whether we can get to Fermat-Little theorems tomorrow. Yeah? Okay. So there is some ways of finding the least residue by some method or by some theorem, which among them is Fermat-Little theorem or Fermat-Euler theorem, which is related to congruences. So probably at the moment we cannot see directly what is the least residue of that big numbers, right? Okay. So a set of integers that are mutually congruent, modulo m is called congruence class residue or residue class modulo m. So when we look at the possible residue, right, for the division of any integer, so the residue, let's say for the example that we have seen previously, which is equal to 1, we have the first one. So among those integers that have at least residues 1, or if you put it in the set, right, all those integers which have the same least residue, the same 1, so they form what we call the congruence class. So in that class or in that set, so 1 definitely is inside that set, and then the next one will be 6, and then the rest will be 1 plus multiple of 5, right? So those are integers which will be in this congruent class modulo 5, which are congruent to 1. And then there are some other congruent class. So how many congruent class can you get for modulo 5? So there is exactly 5 modulo, sorry, 5 congruent class, modulo 5. So basically, in that class, so it satisfies this condition whereby A congruent to B mod M. So meaning that if A is congruent to B mod M, so A and B are in the same congruent class. Yeah? So if we are talking about M equal to 5, so M is equal to 5. So 6 would be in the same congruent class as 1, as 11, and the rest of the numbers, which is 1 plus multiple of 5. Sorry. In the same means that when we divide those numbers in the congruent class by m, so we should be getting the same this residue, right? Which is 1 in our case. Then if x and y are congruent to x congruent to y modulo m, then y is called residue of x modulo m. So it is not the least residue, but definitely for any congruent class, so one is the residue of the other, right? So let's say 6 is the residue of 1, 1 is the residue of 6, 11 is the residue of 6, and so on, right? So as long as the x and y are inside in the same congruent class, so they are residue each other. Okay, so we have a set of integers which the number is m, and this set of numbers is called complete residue system modulo m if for every integer y there is one and only one j, such that y is congruent to rj mod m. So basically it refers to the definition that we have given, which is the least residue, right? So meaning that for any given integer, so it would be congruent to at least one integer in the set of 0 until n minus 1. So the possible integers that can be called a complete residue system is the set of integers which is exactly that we have listed previously, which is between 0 and minus 1. So that set of integers is called complete residue system, because every integer will congruent exactly to one of those integer in the set, which is the complete residue system. So what is the complete residue system of modulo 5? It's a set of how many integers? So we say if our m is equal to 5, so we have a set of numbers which is R1, R2, R3, R4, and 5. So according to the definition, so we must have m number of integers. So we have 5 integers. So what are the conditions for this set of numbers to be a complete residue system? So none of them are congruent to each other. Meaning that Ri is not congruent to Rj, if I j. And the statement we are saying that every integer y will be congruent to exactly one of them, right? So this is a complete residue system. So a simple example would be this 5, right? So this is a complete residue system, modulo 5. Because we know that for every integer, so the least residue would be among these 5 of them, right? So for modulo 8, so possible complete residue system is 0, 1, 2 up until 7, right? Based on the definition. So what about this set of numbers? So are they the complete residue system modulo 8? No. So we have 1, 2, 3, 4, 5, 6, 7, 8. So basically the difference between this set of integers and this set of integers is that we replace 8 by 0, right? So instead of 0 we have 8 here. So can we consider that to be a complete residue system modulo 8? So according to the definition, so it is a complete residue system if any integer will congruent to exactly one of them in the set. So does that apply to the second set? So definitely for the first set it applies, right? But for the second set, so does it also apply? Given an integer, so does it congruent to at least or exactly to one of these? So the difference is only these two numbers, right? So what we can see from the two sets, 8 and 0 are in the same congruent class, right? So meaning that it is congruent to each other, or one is a residue of the other, right? So meaning that 0 is congruent to 8, or 8 is the residue of 0, 0 is the residue of 8. So we just replace a number with an integer which is in the same residue class as the other one. So it still maintain its element of complete residue system, right? So meaning that if you are to have 8 integers in a set, and we replace any of the integers, let's say the 8 integers are congruent exactly to one of these, and if you are to replace any of those integers with integer in the same congruent class, so the set of numbers still maintain, still will be a complete residue system modulo 8. So meaning that, so how many complete residue system that we can have? So meaning that infinite many, but basically the requirement is that it must be from the same congruent class, right? Meaning that we must have 8 integers or 8 elements, and none of them are from the same congruent class, right? Did I say that correctly? No, 2 of them are from the same congruent class, right? Yeah, that's correct. Okay, so are there any more? So definitely there are, right? So we just pick any integers from 8 different congruent classes, so definitely they will form complete residue system modulo 8. Okay, but we are familiar with this set of integers, which is the least residue, which is from 0 until n-1, or 7 in this case. So it is called canonical complete residue system. So it is still a complete residue system, but it's the basic one, right? But we can have any other complete residue system as long as the requirement for complete residue system is satisfied. Okay, so that's what we get from the discussion. So these are some important properties of the complete residue system. So there are infinitely many complete residue systems modulo integer m, and the set of m integers forms a complete residue system modulo m if no 2 integers in set are congruent modulo m. So meaning that they are incongruent to each other. So when you have m integers in a set, so if you can determine that no 2 are congruent to each other, then it is a complete residue system. And what are the integers? What are the elements of residue class or congruent class? So basically, we have this set of numbers, which is if you are given a and m, so those integers are in the same congruent class. So a plus m, a plus 2m, and a plus multiple of m. Or we can go to the left also, right? So in the congruent class, so definitely there are infinite many integers, right? Okay, so some properties of theorem concerning congruences. So given any 2 integers a and b modulo integer m, so we can show that the GCD of a and m is equal to b and m. So basically what it says is that if the 2 integers are in the same congruent class, so definitely the GCD of a and m, and any integer in the same class with m will be always equal, right? So if you look at the example that we have, so we have 6, let's say we have 6 and 5, right? So GCD is 2. So what are other integers that is in the same congruent class? So we had 5, so 11, let's say. So 11 and 5, definitely the GCD is 2. So if we add another 5, so we have 16. So 16 and 5 also have a GCD of 1, right? So this GCD state equal to for any integer a and b, right? From the same congruent class, the GCD is always the same. Okay. Okay, from the definition of the complete residue system, so we have another system which is called a reduced residue system modulo M. So it is a set of integers also. Let's say we call it Ri. So the condition for Ri to be in this system or reduced residue system is that Ri must be relatively prime to M. Okay, so that's the first condition. And then for any given two elements in this set, so it must not be congruent to each other if I is not equal to J. So meaning that it is incongruent, yeah, to each other. So that is the only condition for it to be a a reduced residue system. So we have a complete residue system, which is in modulo phi. This is a simple example of the complete residue system. So what is the reduced residue system? So basically the best way is to get the element from this set, right? So we satisfy this condition, which is must be relatively prime to M, right? Because when we need the element to be congruent to each other, right? We need that any two integers, this set must not be congruent to each other. So definitely this requirement is satisfied in this set, or we have like that. So, but the other extra requirement is that Ri and M must be relatively prime. So, looking at these five integers, so we can identify which one is relatively prime to one and which are not relatively prime to one, right? So, what are the integers that are relatively prime to one? 5. So, is 0 relatively prime to 5? Five zero. What is the GCD? We have discussed this. 5. So 5. So definitely cannot be inside the group, right? So the GCD is not 5. Right? So what about 1? Yes. Definitely GCD is 1, 2, also 1, and up to 3 also 1, and so it's 5. So meaning that we have 4 out of this 5 that can be this set of reduced system, right? Satisfying this condition, and you got and this condition, right? Meaning that we can actually get it from this complete residue system. Then from there we can actually determine which elements are inside the reduced residue system. So phi is easy because it is a prime, right? So basically, we can get it from all the integers which are not 0, right? So what about 6, let's say? So the complete residue system is, so we are taking 6. 6, what we know, modulo 6. So the complete residue system is 0, 1, 2, 3, 4, 5. So this is the complete residue system. So what is this reduced residue system? So satisfying the condition of these two conditions, so 0 cannot be inside the set. It would be similar to this one. So what about 1? So this is the GCD of 6 and 1 is 1, so 1 can be in the set. 2 also cannot be in the set. 3 also cannot be in the set.
5.
And the only other integer is 5, right? There's 5 and 6. The GCD is definitely equal to 1. Meaning that we have only 2 integers out of the possible 6, right? If we are taking modulo 6, and those 2 integers are the only one which satisfy this condition. The GCD with 6 is equal to 1, and definitely 1 and 5 are not congruent to each other, right? So those are the reduced residue system modulo integer M, 5, right? So you say. What about 8? If you were to take the example quickly, so we have 8 set of integers which form a complete residue system, right? Modulo 8. And 8. So what is the reduced residue system? Modulo 8. So basically, looking at this condition, which must be satisfied. So basically, you can only have how many integers in the set? 1,
3, 5,
3, 5, right? So how many integers in the set? We have 4, right? So in modulo 5 we have 2 integers, 2 elements, sorry, 4 elements. In modulo 6 we have 2, in modulo 8 we have 4, right? Okay. But when we are talking about complete residue system, so how many integers do we have in the set? We have exactly m, right? So that's easy enough, right? So how do we decide the number of elements in the reduced residue system? Do you have to calculate every time the GCD of each integer with m? Or are there any special way of calculating it? So we'll get to that. Right? Okay, so some example. So this is module 8, so we discussed already. So we have 1, 3, 5, 7 is the set of reduced residue system, module 8. And module 7 is simple, because why? Because it is a prime, right? Definitely the integers except 0 is going to be prime to 7, or the prime, right? So for any given prime, the reduced residue system is integers from 1 up until p minus 1, right? So we have p minus 1, the number. But for any other integers, so it seems to be not exactly, what do you call that? Not sure about the number, right? So we have 2, we have 4, so depending on the integer m. Okay. Okay, so I think let me answer this one. So what is the reduced residue system modulo 9? So out of the 9 integers, so the only integers which are relatively prime to 9 in terms of the number is 1, 2, 4, 5, 7, 8, 6, right? Is it correct? 6? Right?
yes.
Reduced residue system modulo 9. Because there's a list of integers from 0 to 9. So the only one which are prime to 9 is 1, 2, 4, 5, 7, 8, right? So except this is 3, right? Which is 1, 0, 0, 3, and 6. But the rest are relatively prime to 9. So meaning that we have 6 elements in the reduced residue system 1 to 9. So do we have some idea of how do you get the number? Based on the example. There is a function that, or there is a formula which will give the exact number of elements in the reduced residue system. So, but I won't tell you yet what the function is. But basically, we can actually calculate any number of reduced residue system for any given integer m. Okay. Okay, look at some properties of the congruence concept. So it is either by Gauss or TDC, yeah, so based on what we mentioned previously. So these are the properties that can be easily proven by the definition, right? So the first one would be A must always be congruent to A mod M for any given integer A. So refer back to the definition, which implies that n divides A minus A, right? N divides 0, so that can be apply. A congruent to B mod M implies that B congruent to A mod M, so you just switch the place to A and M, sorry, A and B. and by the discussion that we had regarding A congruent to B, meaning that A and B are in the same class, so they are always congruent to each other. Then A congruent to B and B. If A congruent to B, B congruent to C, then A must be congruent to C, 1M. A is congruent to B, 1M. A plus C is congruent to B plus C. So adding up N C still congruent, still 4. If A is congruent to B, then AC is congruent to BC for any given C. So you can multiply C on both sides, so the congruence still stays. And last one, A congruent to B, 1M, C congruent to D, 1M. So if you multiply A by C, A and C, so it is congruent to B and D, 1M. Then the linear combination also will be true, whereby dx plus cy is always congruent to dx plus d1 1M. So those are the properties of the congruence. So you can actually try to prove it using the definition. Okay, let's look at one of the properties, which is number 5. Which is number 5? Which one number 5? 5 is one, right? So A congruent to B, 1M. So that implies AC congruent to BC, 1M. So the question is the converse true? Meaning that if you have AC congruent to BC, 1M, can you cancel out C so that you get A congruent to B, 1M? Can you do that? AC congruent to BC, 1M implies A congruent to B, 1M. So the other way around, which is from the left to the right, so it is always true. Multiplying by any C, any given C, so it is still true. So what about the converse of the statement? So if you have this, does it imply this? So what essentially we do is we cancel out C, right? From the congruence on each side. So can you do that? For equation, you can, right? So if you have an equation, AC equal to BC, so then when A cancel out C, implies A equal to B. But for congruence, you cannot, right? So you can find some example, or you try to find some example that doesn't satisfy the condition, right? Meaning that you have AC and BC equal to 1M. So if you cancel out C, so it doesn't hold anymore. Okay. But the only time that you can cancel out is when C and M are relatively prime. So if it is relatively prime, C is relatively prime to M, then only you can cancel out C, so that A congruent to B, 1M. So otherwise, in principle, so it's not always true, right? Okay. Let's look at this congruence. Cosine, yeah, it should be a congruent, right? So x congruent to 4 mod 7. So what is that actually? So we have congruence notation previously, but now we have x inside the congruence, right? So we have to x congruent to 4 mod 7. So when we have that x, just like a variable, right? Or in equation we call that unknown. So this is called congruence equation. So what do you do with congruence equation? You solve it, right? So what do you mean by solving congruence equation? Finding x that satisfies the congruence equation, right? So let's say we have this congruence equation which is 2x congruent to 4 mod 7. So basically, if you were to solve this congruence equation, we are looking at integers that satisfy the equation, and the integers that we are interested in is not any integers, but the integers in the set of the complete residue system, right? So, because if one solution, we have one solution from that set, so definitely any integer from the same congruent class will also satisfy the congruence equation. So basically, we are looking at integer between 0 and 6 only, right? So is it possible to find an integer that satisfies this equation? So you can try substituting 0 until 6, right? Until you can find some final solution whereby it is satisfied, right, this question. Let's say 0, so definitely 0 is not the solution, right? Because 0 is not congruent to 4. Then is 1 a solution? So 2 times 1 is 2, so 1 is not a solution. Is 3 a solution? No, also. Right? Because 3 times 2 is 6, 6 minus 4 is 2. Yes. Will not be divisible by 7. Right. 4, is it a solution? 8 minus 4 is 4, so not possible. It's 5 is 5 a solution. 5 2 is 10 minus 4 is 6, so not divisible by 7. And is 6 a solution? 6 to 12 minus 4 is 8, also not possible. Different? Huh? 9? 6, 12. Any solution? 9. Oh, we missed that. Yeah. How can I miss that one? 2 is the solution, right? Because 2 times 2 is 4. So definitely 2 is congruent to 4, is congruent to 4 mod 7. So 2 is the solution. But there is no other solution, right? Except that one solution. But basically we can simply cancel out 2 from these two expressions, right? Because we can apply this theorem for here. Because 2 and 7 is relatively prime. So we can cancel out 2, and we have 2 here. So x congruent to 2 mod 7, meaning that 2 is the solution. So we have that form which is x congruent to 2 mod 7. So that 2 is the solution to that congruence equation, right? So as long as you get x on the right hand side, so whatever is on the right hand side, so that would be the solution, right? What about this one? So you cannot cancel out anything, right? So because we don't have 2 here. But possible to cancel out. So what you do is, because any even integer, right, is divisible by 2. So if we were to get even integer, if you have to replace it by an even integer, so we can actually cancel out the 2, because 2 and 7 is similar to this one, is relatively prime, right? But how can we get an even integer here? Because we have 1 here. So what we do is, we replace it by any other integer in the same congruence class, or basically we just add 7 to it, right? Or multiple of 7 until we can cancel out. So if you add 7 to this, right? Because when you add 7 to the equation, you are actually adding 0, right? So it doesn't change the equation, right? But if you add up 7 here, so we have 8, right? So it's okay. And 8 has 2 as a factor, so when you cancel out 2, so you have only 4, right? Left on the right hand side, so meaning that the solution is x equal to, or x congruent to 4 mod 7, right? So we can check whether that is correct. So it is, right? So we multiply 4 by 2. So you have 8 minus 7, which is divisible by 7. So that is the solution to the congruence, which is, we have only one solution. Okay, so the last theorem, we can cancel out C from the congruence equation if it satisfies this condition. But if it doesn't satisfy the definition, whereby the GCD of C and M is equal to D, right? Which is not equal to 1. So what we can do is that we can cancel out C, but we must divide M by that GCD. So what happens is that we have another congruence equation, but basically the modulus is now M on the D. But still, from here we can actually, yeah, I mean, this is, okay, we can start, right? So if we know what the GCD of C and M is, right? So we have this new congruence, which is A congruent to B over M over D. So in congruence equation, so basically you can do the same thing whereby if you are, say, given this congruence equation for x congruent to 4 mod 6, and you know that C and M, which is 2 and 6, right? The GCD is 2, so we can actually divide. We can divide 2 from each of the terms here, which is divide by 2, divide by 2, and divide by 2. So we have 2x congruent to 2 modulo 3, right? So basically from there we can actually solve the congruence equation after we have solved the reduced equation. So same thing can be done here, which is 30x congruent to 27 mod 33. So the GCD of 30 and 33 is equal to 3, right? So we can cancel out 3 from each of these. And we have a new equation, then if we want to solve that equation, so we can actually get the solution for the original equation. Okay. Any question on congruence equation? So we have some exercises which some of them probably from the properties that we have stated previously. So show that A congruent to B mod M implies that A squared congruent to B squared mod M. Is the congruence true? Meaning that from here to here is it true? And then number 3, show that 10 to the k is congruent to 1 mod 9 for all k equal to 1, 2, 3, and all the integers, which is basically simple to show, right? The second and third one. So basically what you want to show is that 9 divides 10 to the k minus 1, which is always true, right? Because that's the definition of the congruent, right? Which is m divided a minus b. So that's m divided a minus b for ak, definitely, right? And then the rest, so we can try to go. Okay, this one shows that every integer is congruent to the sum of its digit modulo 9. So this is an interesting question. So given an integer, so look at the digit. If you were to add up the digits, so it will always be congruent to the sum. So the number itself, right, is always congruent to the sum modulo 9. So, for example, so we have, let's say, right? So 26 of this is 9. So 27, right? So 27 is definitely congruent to the sum of the digit, which is 2 plus 7, 9. So when you get 9, we'll always go back to the 7 minus the sum. So that's how the question is. So that is always true for any given integer, as long as the sum of the digit is over 9. So the integer is the integer is congruent to the sum of the digit modulo 9. So meaning that 9 is divisible by, or 9 divides the integer minus the sum of the digit. And rest here actually congruence equation, so we can actually try to find the solution to those equations. Okay, so I don't think I can finish this topic, which is linear congruence equation. So I think I'll stop there. So I probably will continue tomorrow. Any question? No question? Okay, thank you.